Let's talk about limits, inequalities, and the squeeze theorem. This is usually something that comes up when you start learning limit laws, principles of limits, and a lot of those are very algebraic. And you get a feeling that limits are fundamentally about doing algebraic manipulations, and I want to point out that's really not true. A lot of functions are given by algebraic formulas, and you do some algebraic tricks to massage them into a form that's easy to take the limit. But limits fundamentally are about things getting close to each other, approaching each other. So sometimes about going up and down, like plus infinity, minus infinity. And so you can often say something about limits without formulas. So one thing that you get an experience of usually with most books is making graphical arguments. Like, here's a graph, what do you think the limit is? And that's great for conceptually, and it's pretty valid, but most people wouldn't consider it a super rigorous way to prove something. Now I'm going to draw a lot of pictures to get the intuition in this video, but there's a nice tool that you can sometimes, a couple of tools you can sometimes use to say some things about a limit, and sometimes to actually prove a limit has a certain value that aren't algebraic. That's the situation. Let's look at the situation first where we actually don't need to know precisely what the limit is, but maybe some sort of qualitative information. In particular, we'd like to have some sort of inequality. And that's something that usually in the curriculum we don't say nearly enough about how valuable inequalities are, but they really are really helpful. So for example, is the limit of some function just positive or negative? Am I going to end up with positive cash flow or negative cash flow? I mean, again, is the aircraft going to end up above the ground or smashing into the ground? It's pretty important. So the fundamental principle there is really basic. Suppose we have two functions. It's about comparing. Inequalities are all about comparing things. Suppose we have two functions, f and g, and what we know is that one of them is smaller than the other. F of g, let's say, is always smaller than, or let's say smaller than or equal to, g of x for all x at least near some fixed point a's, which is where we're going to take the limit. Since we're going to take the limit at a, we don't really need to know or care about what f and g do away from a, but we'd like to know that this relationship holds for all x near a. So for example, let's say a was 0 in this picture, and I'm not sure what the heck this crazy function g does away from this graph, but looks like near 0, it looks like f, let's say that's the bold function, is always less than or equal to g. Here, note that f happens to be much simpler than g, and that doesn't have to be true for this theorem to work, but we're going to see in the elaboration of this, it's really going to be useful if there's a distinction between the complicated function you want to analyze and maybe a simpler function that you already know something about. So let's think about it that way. So here's the thing. If you already know that both limits exist, which is a big if sometimes, then if g, this thin line here, is always giving you values above the values of f, there's no way that the limit of those values can end up under the limit of f. So you can prove, if you look at the very careful methods of proving with limits, that the limit of f as x approaches a is less than or equal to the limit of g. So that's just a very simple principle. It's pretty easy to remember. If f is smaller than g, their limits have the same relationship. Now, we can take that a little further. Suppose we have three functions, and f is always less than g, is always less than h, at least when x is near the fixed value a. Okay. Now, here's one version of it. If we know all three limits exist, which might be like, oh, whoops, maybe I don't know that, but assuming that we know that, then we just use the same principle twice. F was smaller than g, so their limits have the same relationship. G was smaller than h, so their limits have the same relationship. And here's the situation where that starts to be really useful. Suppose g is a complicated function that is really hard to calculate the limit or say anything meaningful about it, but I realize that there's a simpler function f and another simple function h, that squeeze it, or that at least sort of sandwich it together. And so g is always in between. That at least lets us say, assuming we know the limit exists of g, we can say something about where it is. So here's a sort of pictorial example. Suppose h was the top function, f was the bottom function, the two bold, and notice those are really simple functions in this case. And then we have some crazier function g with lots of bounce and wiggles, but we know that as long as g is known to have some limit, that limit has to be in between the limit of f and the limit of h. It is sandwiched in here and constrained by those two guys. So that's a little disappointing for a couple reasons. One is we had to assume that the limit exists in the first place. And second, all we get is some inequalities. And we can actually refine this pretty nicely in a certain situation. So here's the deal. So for example, in terms of the drawback about the limit maybe not existing in the first place, we could equally have this picture. I have exactly the same simple functions, f and h. Now, unfortunately, g has similar wiggles, but oh gosh, it's one of these really nasty wiggly functions here. It's hard to tell even on a computer graph exactly even what's going on there, because the computers don't graph functions with infinite wiggles very well. Even if let's zoom in, this was going from -1 to 3. If I zoom in actually pretty tightly from -0.1 to 0.1, now we see I've created a function g that just has the wiggles just never stop. They actually get tighter and tighter and tighter. And in fact, even in here, the computer's doing a pretty crappy job of graphing it because it's so variable. So this is a situation where you still have the hypothesis that f is always less than g is always less than h, but that doesn't force h to g to have a limit. There's still too much room for it to do that kind of crazy wiggliness. But, okay, here's where we're going to get to the squeeze theorem. Sometimes called the sandwich theorem, but I'm realizing actually sandwich is kind of like the situation we're having here, but squeeze is really a better word for what we're going to have in this stronger situation. So suppose we know that f is less than g less than or equal to h. Again, it's most useful in the case where f and h are simple functions that you can calculate a limit for, and g is something more complicated that you really don't know how to calculate it with sort of algebraic techniques. Okay, and so again, all that only has to be true for x near the a where you're taking the limit. And let's suppose that the limit of f is known to exist, the limit of h is known to exist, and they're equal to each other. Now what is the picture? So now we have these bold lines, f on the bottom and h on the top, and as you go into a, what we're assuming is that they have these limits and they squeeze together to be the same limit. Now, that's a big thing to assume. It won't always be true, but it's really nice to recognize when it happens. And now look what happens. With g, it could wiggle a bit out here, it could wiggle a bit out here, but it just does, it gets less and less room to wiggle in here. It certainly looks like it's squeezed down so that the limit of g actually must exist. We've proved it exists even though we really don't know exactly the details and we don't have a formula for g. That's very powerful. And that limit has to be the same number. So it looks like we've proved that the limit of as x goes to a of g of x exists and is equal to L, the common limit of f and h. And that's absolutely true. It's the squeeze theorem. Some people call it the sandwich theorem. But yeah, the squeeze theorem is probably really a better name to really emphasize the squeezing down to no wiggliness, the no variability. We don't need to know the algebraic details of g. We're going to need to show that it has that squeezed property. G could be a very messy function because we only need to understand some inequalities. And often you need that's much looser and more powerful than trying to show an equality. Okay, we do need the two squeezing functions. And usually we want those to be as simple as possible so we can calculate the limits. All right, so finally an example. Let's see, what's my time? Tell you what, we'll do that in a part 2. We'll do an example and then a non-example, something where you might think that these ideas, some similar idea might work, and we'll show a little bit of a pitfall.